So I'm Mike Cohen. I'm a director of product management at Cisco. I joined Cisco through its acquisition of NCMA Networks. So I worked on the NCMA product line, which is now the Nexus 9000 and their application-centric infrastructure products. So what I'm going to be talking about is related, but not directly, not directly tied into that product line. I'm going to be talking about how we were thinking about managing infrastructure that helped us develop some of our products and also is driving some of the work we're doing in the open source community around it. So let me start by laying some groundwork about how we thought about networking. And really, we looked at networking and it was really sort of a set of micromanaged infrastructure. You're giving very low-level specific commands to a number of very complex devices. And networking configuration essentially became an art that was really divorced from what the application wanted. That ended up getting dissected into these very small pieces, that were compiled in networking jargon, essentially, and programmed in different ways. And that really created a number of problems around scaling, change management, coping with failures, interoperability across devices. We saw all these issues, and really, even as kind of the software-defined networking world came on, it didn't really resolve many of them. It actually, it moved them to different places. It moved them between different domains of who managed them, but it didn't really solve them. So if you take kind of a broader step back, and you think about different kinds of control systems that might manage infrastructure, we sort of broke them down into two classes. There's imperative control systems, where there's effectively a big brain in the infrastructure. It knows how to speak to everything. It knows all the low-level commands about how every device works, and someone would give it a high-level instruction, like launch an application, and it would break that down to very specific commands. In networking, that might be a VLAN or an ACL or configuring a route somewhere. But there's analogous versions for servers and storage as well. But you really need this big brain. It needs to know how to interface to everything. We looked at it from a different way, and we actually thought about an alternative model of declarative control, and effectively something called promise theory, where the idea is to allow high-level commands to actually be passed down all the way to the edges of the infrastructure. So the devices are smarter. They're given a high-level command that actually maps to what the user ultimately wanted, and then they're allowed to interpret it based on how they work. Now, this has a number of interesting, properties around scaling and resiliency, because a lot of your intelligence ends up at the edge, so you can actually cope better with a lot of different issues in the network. And all you need to do is pass back a fault if you can't honor the high-level command that you got. When we think about how we're building our products, we actually lean towards this direction of declarative control systems. And we actually believe this is a good way of managing infrastructure in general, and we're driving some of these ideas through OpenStack and other elements of open source infrastructure management. So I mentioned what's cool about declarative control. There are a number of advantages. The idea is using a voluntary cooperation of agents that essentially publish their intentions and commitments to each other. So it's an abstract. It's the passing of abstract policy all the way down to edges and smart devices. Now, one of the big advantages you get here is scalability. You no longer have a central manager that gets increasingly bigger and more complex as it deals with more things. It really just has to capture what a user ended up asking for and relay that down. You get very good resiliency, because if your management system fails, it's actually okay. All of the edges of the network already know what the policy is, and they can be busy continuing to implement it and continue to keep things running. And if one of those edges fails, all it needs to do is grab its policy and replay it, and your system is back to a working state. You get very good interoperability characteristics, so you can deal with different versions of software on devices, different, slightly varying devices across multiple vendors, because everyone's given the high-level, request, a high-level abstract policy, and they're allowed to render it however they choose. You can actually normalize pretty well across devices without effectively dumbing down what the devices can do. They can all expose their feature set, but they can do it by taking an abstract policy and rendering it into something more concrete based on what they can do. And ultimately, there's also kind of an ease of use argument for people that manage infrastructure. They end up with effectively a self-documenting system. So what they ultimately asked for when they launched an application, that policy is captured directly in a manager and is distilled down to the edges. You don't get artifact behaviors, right? If I turned off the application, I turned off 80% of its configuration, left 20% by mistake, maybe because my cleanup job failed. It's hard for me to go and figure out what that 20% was. They might hang on for a long time. I might think it was doing something else. You lose the documentation of what actually happened and what you distilled down. With this kind of behavior, you don't. All the edges know, the policy is removed from them, and they can undo all the configurations. You get a very clean behavior as a result. So the question was, declarative control is cool. That's great. Well, what's a policy? How do we represent that? What are you even talking about? And that was a pretty hard problem. And that was actually, when we were doing NCMA, that was actually one of the big pieces that we spent a lot of time on, right? Independent of building hardware and switches. Well, what's a policy for managing infrastructure? Particularly focused on the network, but hopefully not limited to it. And how do we get at that a little more distinctly? So, first we started with kind of breaking it apart into a three-service problem. So your cloud management system has a couple different inputs. One is your user intent. What is the person who's launching the application? What did they actually want you to do? What parts of the application can speak, to each other? What kind of behaviors do they require? Your operational requirements about how your underlying system works, and from kind of an operator perspective. And you have infrastructure capabilities, right? My hypervisors support this much CPU and RAM, and my storage, my storage this large and it's accessible in this way, and my networking, it's kind of bandwidth and QoS support. So that's another set of inputs, and ultimately you need to munge all these things together and produce, a state of the system. So kind of when we were thinking about policy, we said, well, let's focus at least initially on user intent. And from the purpose of this talk, at least, I'm going to focus on that part. Is how do we at least capture what the application writer wants when they're describing their network relationships, without asking them to go take a course on networking and understand VLANs and subnets and VRFs and a bunch of networking constructs that aren't really natural for them. So. Again, this was the problem we focused, we kind of focused and zeroed in on. So, so what does that look like? So we started taking a step back and we said, well, what does communication between, kind of different people look like? So let's say you have two entities, in a system. And, for example, you kind of, she might say, I can speak French and I can speak about bees. And, the counterpart would then go ahead and speak to her in French about bees, right? Because that's what she can speak about. So when you model that interaction, what does it really look like? Well, the two entities agreed effectively on a contract about how they communicate, and a couple subjects within that contract that they can specifically speak about. And you can even be more explicit, and you can say, well, one of them, one of these kind of groups or your individuals, exported the contract, said these are the things I can speak about, right? I'm providing you this interface to me. And the other one consumed it and said, okay, I will speak to you over that interface that you've allowed. So that's how we actually arrived at some of the fundamental primitives, right? We actually almost captured them right here, right? There's a idea of effectively endpoints, contracts about how they interact, and the subjects they speak about. And then things obviously get more interesting. You may have taboos, things that she doesn't ever want to speak about, and that also could be part of her contract. And this naturally maps to sort of a provider-consumer relationship, but and it scales out across groups. So instead of one endpoint, why can't this be a group of things with the same policy? Think of it as an application tier, maybe. But this can also be a symmetric relationship, though, where peers communicating over essentially speaking about a set of things. So that was sort of the logical framework we developed, right? And that was kind of the starting point. We said, well, how do we start mapping this into something we can really use? So next problem we have to think about is, well, what's an application? If we're going to if we're going to map that to applications, we've got to start defining what an application is. It's not a VM. That's clearly not enough. But so what exactly is it? So really, it's an interconnected set of components, right? In the three-tier app world, you have web app and database tiers. They may be VMs, they may be, they may be sets of physical servers. At the end of the day, they're, to some degree, they're endpoints, right? They're individual distinguishable elements. Now they connect to the internet, and they connect to each other, sometimes over a private management network. And they're broken up into tiers, and to some degree, you could think of them as protected by a membrane, right? Something that defines how other things interact with them. So, this is sort of our basis of an application, and that's where we started mapping. We started mapping constructs out of this logical framework. And as I go through this, I'll actually end up back at this three-tier app and say, okay, well, of the constructs we got, how do they map into this? And I'll kind of show you that as I dig in here a little bit more. So first is, we had this fundamental idea of an endpoint. Well, so what's an endpoint? But at the end of the day, from a network perspective, it's something we can switch on, right? It's something discernible. It's something discernible in the system. It could be a NIC, physical NIC, virtual NIC, but it could be a MAC or an IP address. If as we start improving some of the switching technology, it could be an LXC container. It may even one day be able to be a tier of an application, not set, like a process, right? You can imagine the OS switching between PIDs, right? The operating system understands the difference between those processes. Why can't we enforce some policy in how they communicate, right? Over IPC mechanisms and other things. Just, basically, an endpoint is something that you have a primitive to be able to separate out and be able to stick a contract in between. Again, from a network perspective today, primarily you're looking at kind of VM, physical NICs, virtual NICs, but it's really a more general concept. Now, what you really want to do is start grouping those things together. If you go back to the application model we had, most applications are effectively tiers of things that all do the same stuff. And those tiers effectively all have the same policy. So fundamental to the model we came up with was, was this idea of a group. Everything is a group. It may be a group of one, but the idea is you create a group abstraction. Everything operates on that on that abstraction of a group. And this is actually a very powerful concept because it has a lot of benefits as you look down the line to things like automation tools. You're no longer automating per endpoint. You're actually automating on a group, and that naturally cascades down through your system. So, it actually has very, very good scaling automation capabilities. If you need to change a policy, you change your policy on your group. Every machine naturally inherits it. So we made this kind of a very fundamental primitive that all our endpoints have to be grouped together, and the groups are the things that we deal with from a policy perspective. And what common properties do they share? So they have to share connectivity, security, access control, quality of service, layer 4 through 7 services that they interact with, so these are the things we actually captured today as part of what we did with NCMA. Although the model is really extensible, right? You could imagine this mapping to storage requirements of how and what storage can be reached, server requirements, right? The BIOS images, et cetera, that might be required. So you actually have a very rich set of policies that actually define what these groups can be. More general performance requirements about how they interact. But the idea is all of the endpoints in the group effectively have to be they have to look the same. And that's kind of the base concept this is built on top of. And then, as I mentioned, this can kind of flexibly map into application tiers, VLANs, kind of you can pick up the security group construct as to some degree a subset of this idea. ESX has a port group concept, which was effectively designed, it really maps to a VLAN, but it was effectively thought of to be this, right? A set of VMs that are all the same. So, that's where your kind of groups come into play. And then, we mentioned you create policies, and policies sit between different groups. It's to some degree as simple as that. When groups interact, they have to interact over these different policies that define how they behave. So then we kind of inserted the notion of a contract. So contract is the thing over which our different groups communicate. Contracts would consist of effectively sets of filters and actions. So if you think of it from a networking standpoint, these can be, I'm a web server, you speak to me over HTTP, and kind of the action there would be to effectively forward traffic. Some other actions might be, span traffic out to a different port, or forward traffic to the firewall before you forward it to the app servers, right? So you can get slightly more complex action sets, but the idea, here is a filter, and then, what do we do if we match on that criteria? What do we do? From the model we thought of, we thought of this inherently as a whitelist model, where effectively, unless you match a filter, you don't really do. You essentially drop the packet, or you don't allow connectivity. That's not so fundamental to this model. You could think of you could do it with an allow deny model. It just makes a lot of things more complicated. Right. So this is the idea of subjects and actions about how they communicate. So now let's get back to the 3-tier web app and actually talk about what that ends up looking like. So basically you end up with 3 different groups, kind of web app and database, right? And these may be populated by VMs. And the mechanism you populate that, right, is to some degree outside the scope here, right? Somehow you're either feeding a segmentation ID in, you're giving lists of NICs or MAC addresses. Somehow you're populating these groups. Each of the group would provide a contract that describes how you speak to it, and that contract needs to be, built off of what it actually does, right? So the web group would export HTTP and HTTPS. The app group might support, expose RMI, for example, and the database group would expose, SQL ports that you could speak to it, and then you'd create consumer relationships. Effectively allow one group to speak to the other over the contract. Now, to make this kind of complete, nothing is as simple as that, right? You start saying, well, now they have to get outside, so now we have to, we effectively have to model things that, live outside of our domain, right? This is kind of how you think about the WAN environment, or you're kind of getting outside of your data center. You probably need a management contract because they also speak, to their management infrastructure. So model that as well. They consume some kind of shared services, so there's probably a contract there for consuming and reaching shared services. And then you optionally, or you either implicitly or explicitly map them to some network constructs. And this is necessary for the purpose of kind of mapping to legacy networking behaviors. So there was a concept of a context, which networking speak is just a VRF, but really is could also be thought of as a tenant. But the idea of a fully isolated namespace. You may also want to expose kind of what I'm calling here bridge domains, but they're effectively broadcast, places where broadcast behavior is enforced, because some apps require broadcast behavior. Some don't. A lot of cloud apps do not. But you want to be able to explicitly say that things in this area require a broadcast semantic, and I need to be able to map that. Now, these don't have to map one-to-one. I'm showing kind of a one-to-one mapping of the bridge domain to group. That doesn't actually have to be the case. Groups can be, you can actually have one bridge domain spanning the entire thing. You can do more flexible things from here. This is probably one of the more common ways you would use it, though. So that's kind of very briefly, kind of from a policy perspective, the way we started breaking down application policy and get as a very an initial framework for for exposing a simpler way of managing infrastructure and managing networking. This is by no means kind of the end of the story, right? If you look at kind of where we got here, we essentially modeled effectively kind of through layer 4. We were able to do what would be like VLAN subnets ACLs style behavior with this model. Now it can be we can get much further. There's a second set of slides that I can kind of go on for a long time here about, well, how do you think about network services, right? So one of the more obvious ways to think about network services is to say, well, between these groups, when one consumes the other, we can force traffic through a stream of network services. We can also model those network services in via these abstract policies, right? So you push through a firewall. We don't care what brand of firewall that is, but it has this set of abstract policies that firewall vendor effectively knows how to implement. We can effectively offer a model allowing people to dynamically insert services as part of their application requirements. So you no longer need to configure the right IP address or anything like that. You would say, these are the tiers of my application. This is how they interact. These are the services I need in different places. Go, right? That's sort of the model of operations we were thinking about, and we wanted to be able to achieve as we were kind of designing the system we were building. But we also, again, this is something we think is generally useful in the open source community. So let me talk about how we took that model. I'll talk about NCMA and kind of our product line a little bit at the end, but I want to talk about how we took that model and what we're doing with it in open source, because there's nothing about this model that is tied to Cisco or even tied to tied to the products we even built. It's an abstract model for modeling application requirements. So where we started looking across the open source software stack and saying, well, where can this add value? At kind of the cloud orchestration layer, if you think about OpenStack, it can add a lot of value in actually allowing users or tenants to author application policies, actually create policies that map to the way their applications really work. And this has a lot of implications for Neutron. Neutron already has an abstraction API. This is not it. So there's a lot of kind of coalescing that needs to happen there. And we're working with that community to figure out exactly what that looks like. But there was still the idea of, well, OpenStack can also expose this kind of declarative approach. This would be a path to it. So that's how we thought about approaching OpenStack. We also looked at OpenDaylight, because obviously we had, in CMA we had built a controller and a system, but it wasn't open source. It was a Cisco product, so you had to buy that to use this, and that didn't make much sense either. So we also went into OpenDaylight, and we said, well, how can we expose these things in the OpenDaylight world? So if folks are not familiar with OpenDaylight, it's an open source SDN controller. Originally started by Cisco, IBM, Citrix. Red Hat's very involved in it. It's actually, it's a very young project relative to OpenStack, but there's actually a reasonably growing community around it. So the idea there was to also expose kind of a policy API, out of the SDN controller, and let that sort of function as managing all the endpoints and doing what SDN controllers were designed to do, understanding where endpoints are, et cetera, and then also being able to push this policy down to different devices. The last place we're looking at kind of working with is going to Open vSwitch and saying, well, Open vSwitch today is effectively an OpenFlow switch. So it's you can almost think of it as like it's a big hash table for that does OpenFlow. But it could actually be a fair bit smarter, and actually allowing it to accept a policy and render a policy directly. Itself could be an interesting capability that would allow it to function in a declarative mode as well. So we're also looking at how we can make some contributions there. So more concretely, what do these things look like in OpenStack? So our group submitted a blueprint, and we're currently working with Neutron to essentially create what we're calling kind of a group policy model and group policy APIs. So these will be initially extension APIs out of Neutron, or at least that's the way we're proposing them, that expose this kind of model, in addition to the standard Neutron model. And this model is necessarily abstract, so it can be mapped into what Neutron does today, but it could also be passed directly via plugin to a backend that would want to interpret it. So that's sort of our starting point in how we interact with Neutron. The idea is to be able to support any kind of network backend, but have this kind of policy model come in on the front side. Now, this is not something Cisco is doing by itself. We actually have a large number of partners kind of helping us drive this effort. Some of them are people Cisco competes with in the market. These are startups that are running in similar but maybe slightly different directions from us. So it's a very it's pretty diverse group actually that have attached to this idea. The reason it to some degree looks very vendor friendly as well is it gives vendors room to innovate. So by increasing the level of abstraction in the API, you can actually get more out of your underlying network infrastructure because it has more flexibility in how it implements things. Current Neutron essentially exposes VLANs and routing behaviors, and that's what networking does today. And it was a very natural place to start, but by creating a higher level abstraction there, you can still do networking, VLANs and routing on the back end, but you're not actually constrained to it. So if you, for example, an overlay vendor or an OpenFlow vendor, you can actually do completely different things. As long as you honor the semantics of the policy I was talking about, you have a lot of flexibility in how your network works. So the next place we started working was OpenDaylight. So here we said, let's let OpenDaylight do what it does best, which is be an SDN controller. But we'll also expose a new API, a new northbound API that looks like this policy model, right? So someone can express the policy they want into OpenDaylight, and then allow OpenDaylight to speak across a number of backends. And you can see how this might fit in with the OpenStack piece, right? Because there's already an OpenDaylight plugin for OpenStack. You could actually use this as the backend here. Now, what OpenDaylight is already good at doing is actually, rendering. It has OpenFlow drivers already, and people are adding support for kind of other vendor extensions and southbound APIs. So, one of the other ones that we worked with really closely with it was the Plexi team around Affinity. This is it's one of their southbound APIs. So we can actually take in policy and we can render it in several different ways. One would be kind of a native rendering, just pass it down to a backend that understands how to deal with policy. But you can also morph it, essentially decompose it in the imperative style I talked about, and send it down to OpenFlow switches or down to some other network backend. You can bring your own southbound here to interpret how this might function. So this is a project that's going on. We're actually working in the OpenDaylight community around it. And it's kind of a similar idea to be able to support multiple network backends. So this is work we're doing with IBM, Red Hat, Intel, Plexi, and Middlecore have all been really involved along the lines here. This is just a quick kind of picture of, well, what are we actually driving there from kind of a data model perspective for people that really want to know, how does this work? If you think about the pictures I showed before, this is very logically similar. Some of the names are different. A lot of them are the same. But we really kind of captured this idea of groups and contracts and subjects, and then filters and actions. That's sort of the core model. And that's what we're building something like that directly in OpenDaylight as a starting point for sort of beginning the process of driving some standardization and coalescing around a model here that describes application behavior. So that's where we're using this forum to start laying out this basic object model. Obviously, this has to be the same as what happens in OpenStack, or it's not we're not going to be producing a very useful system. But that work is we're doing our best to make sure that works out as well. This one I'll spin through a little more quickly, depending how many folks are interested in kind of from an architecture perspective. What this ends up looking like again is a northbound API from OpenDaylight that actually can take in application policy, and then OpenDaylight already has a number of kind of endpoint registry kind of inventory services that know where different endpoints are. And then essentially what it would do is be able to either decompose this contract relationships that I described previously, render them down into flow, OpenFlow or CLI or Netconf for its existing southbound APIs, or pass them along natively directly, you're directly out of the system. So essentially what you get here is a very flexible service where you can use this model in a lot of different ways, regardless of what network you have. So that's the quick story, at least, on how we're driving, both on the model and then how we're driving the model in the open source community. These are all activities we have ongoing. We'd love, we have groups going on with each of those projects that sort of meet publicly. If anyone's interested, come chat with me after, and I can help you guys get plugged into the work that's going on. The last thing I'd like to do is tie all this back to, well, what did Cisco actually build out of this, and how does this fit in? How does this fit into the system we created? From kind of an NCMA perspective. And so I want to give you a quick, just a quick briefing on what that product actually is, and why that's interesting. Cisco, as part of NCMA, what we created, when we joined Cisco, we created a product that's called the Nexus 9000. So this is the newest line of Nexus switches. The interesting thing about these switches is they run in two modes. One is what we call kind of optimized NXOS mode. So this is, think of it like it's a standard switch, better hardware, better programmability, better power efficiency, better reliability, but all the standard protocols you would expect to find in a kind of a Cisco Nexus switch, it achieves them, at a better price performance. These switches can also be flipped into a fabric mode. It's an operating system change, not a hardware change, at which point they run alongside a controller, which we call the APIC, the Application Policy Infrastructure Controller, which looks not wildly unlike the OpenDaylight picture I exposed, but a little more purpose-built to accept policy and push the policy down into an underlying network. And then we also married this with a policy model, and that's effectively what I've been speaking about, this idea of being able to model application behavior and render it in the network without doing any per-switch configuration. So this is the solution. This is the solution we built and we're bringing to market. If you think about the way it operates, someone creates the policy, actually goes to the APIC, and the APIC distributes it down to the edge of the network where it gets enforced. So this is where the declarative elements of the policy come in. So the high-level policy is actually pushed down into the switches, and the switches understand how to render it into the native capabilities they have. So there's no configuration of what VLAN or what VXLAN tunnel is put in a particular place. None of that happens. You just push the high-end, the abstract policy down into the network. Again, this is the same idea we're driving throughout the rest of the infrastructure. The product, more in kind of the fabric itself, it's a VXLAN fabric, 40 gig non-blocking, fully integrated overlay and underlay. The fabric also has a built-in line rate directory. So part of making this model work is knowing where different endpoints are. If you look at my picture, it was, can two endpoints communicate? That's part of the policy. Well, how do you enforce that policy? You've got to know where the endpoints are, because the packets talk about MAC addresses and IP addresses. You've got to be able to do that mapping. So in our fabric, we do the mapping directly natively as part of the solution. There's no reason in an open source solution we couldn't do it externally in an OpenDaylight or in kind of some remote server. In this solution, it's fully line rate, fully integrated, complete uptime even when the controller is disconnected. So you get very good resiliency features out of it. System was designed to scale up to 1 million endpoints and 64,000 tenants. And was also designed to, I mentioned, be an integrated overlay and underlay. So the other very key feature we designed around it was this concept of telemetry. So being able to give you very, very deep visibility from a hypervisor all the way through the fabric. So we can give you detailed statistics of latency, of packet drops, of paths that are being taken. So you actually get a full set of telemetry across the system about how things are operating. So instead of having, if you think about kind of an overlay-underlay world, you end up with two different networks. You have to manage them, you effectively manage them separately and deal with problems on them separately, and you end up with a very tough telemetry problem. Here we've integrated the things together, so you have none of those issues. Another big advantage here is since we can handle all the encapsulation inside of Fabric, we can be completely hypervisor agnostic. So this can work across VMware, Microsoft, KVM, and bare metal servers, right? We can take any kind of encapsulation, and we'll be able to normalize it at line rate without any issues. And these are all kind of interesting properties of the fabric here. I mentioned when we were doing the APIC, we were thinking about everything from an open API perspective. So this is what's helped us actually drive a lot of things into the open source community around policy models and and policy to device interactions. So essentially what we built, we built a number of different APIs. One was a REST API, lets you do full policy configuration. So if you think of the way this policy works, everything is really an object. These endpoint groups are objects, contracts are objects, filters are objects inside them. Essentially it's just a tree structure of objects. We fully expose that structure, and we allow you to configure anything directly via REST. Fully enough that we built our own UI directly on the REST API. At the same time, so that's driven a large ecosystem of partners that have attached to this across orchestration tools, hypervisors, monitoring tools, storage vendors. They've all been able to plug directly into the system. At the same time, we're thinking about how we open some of the open and standardize some of the southbound components. So there's actually two interesting kind of APIs there. One is kind of what I'm calling a fabric attached API. Essentially, it's a mechanism for sharing policy between a controller and a switch, and being able to share that in its kind of native abstract form. But we've also created kind of a, effectively a scripting, we call a scripting interface to work with layer 4 through 7 vendors. So we saw a very acute need for service chaining behaviors to be able to directly interact with network services And people wanted it immediately, right? They wanted to use the services they had, the investment in F5 that they made, they wanted to preserve. So we built a scripting interface that actually works with all the APIs on those boxes directly as is, and enables them to be incorporated into the policies I was describing as service chains between different groups. And this is a native capability, exposed through the fabric, but also exposed through the policy model to describe how service chains should behave. So obviously, as we're doing work with OpenStack and other systems, we're trying to, we're trying to bring that service chaining, behavior into those systems as well, with a pluggable backend that different people can operate on. But our goal in doing this was to create an extremely open system that really allows everyone to come and attach and interact in different ways. So that's a very quick overview of what we've done with ACI, and I think that is more or less where I kind of conclude from here.